Welcome back. So we are looking at vectors in calculus, some definitions first, because there's some notation that we just need to get under our belts, and then we'll look at some stuff and examples and stuff and things. The cool thing about vectors is that we get to have a magnitude and a direction. So instead of just thinking about having like a particular distance that is happening with some of our motion things, that we also have like another way of showing how like we can be more specific with vectors, which is pretty cool. And vectors are also going to be super useful as you learn about more dimensions, like the different kinds of coordinate systems that we have for modeling things. So yeah, we're not going to be able to get into it super deep in this class, but it is very cool and coming soon to a calculus class in the future for you. So let's get started. We have scalars and then we have vectors. A scalar is a number, a real number for the purposes of our course, and it's just a number. There's no other information that you get along with it. A vector is a directed line segment with a magnitude or length and direction. So this is Vector from the Despicable Me series thing, and he is the magnitude with direction, and that is what a vector is, where you have an initial point, where you have a starting point, and then you have a terminal point. So the distance between those 2 points is the magnitude, and then where you're going from your initial point to your terminal point is the direction. All of these are equivalent directed line segments. So they are directed because they have an arrow. So there's a demonstration of the motion. But they're all equivalent because they're all the same length and they're going in the same like trajectory. It's just that where they're starting and where they're ending is different. And so they're not the same in terms of like exactly where they are. However, they have the same magnitude and they have the same direction. So they are equivalent directed line segments. This is a directed line segment. This is a bunch of different directed line segments that are all grouped together. When we're writing vectors, there's a lot of different notations. But in general, if you're reading something that's bold, so these are all bolded, then that would show a vector. If you are looking at handwriting, then giving a little arrow on the top for vector U, vector V, and vector W, with all those little arrows. It's kind of a half arrow. Some people, when they do it, they go like that. I just find that takes too much effort, and this gets the point across. And you'll probably see this more often than this. But I guess it also depends on who you're working with. Boldface and little hats, little arrow hats. How can we write out vectors? So if you're looking at a vector with an initial point at the origin, so that's at 0, 0, right? And your terminal point is at the point v1, v2. So you're going from 0, 0 to v1, v2 as your terminal point. Then you can write in component form the vector v with these like sharp brackets, taking these points or taking those scalars, and then you just put sharp brackets around them. I think in LaTeX and stuff it's like wrangle and langle, but don't quote me on that. But maybe it'll work in Kami, not sure. But you're putting going from 0, 0 to wherever you're going. That's what's in here as your, I guess, like coordinates. But that's the component form of your vector v. And we also have the 0 vector, which we use often. 0 vector, if you're handwriting it, it's a 0 with, again, the arrow on it. And that is going to be the vector just to the origin. This is magnitude. So the magnitude of a vector is taking the terminal point minus the initial points for the first coordinates difference squared plus the terminal point minus the initial point difference squared, and then adding those together and square rooting. And this should ring some bells because you're basically looking at the Pythagorean theorem, right? Because you have this is our change in this direction, and then this is our change in the vertical direction, and so you get the magnitude. Magnitude is there. We also have standard unit vectors. So unit meaning one, like unit circle, or we're looking at, a circle with radius 1. So we have unit vectors, where we're looking in the horizontal direction for I guess I should do a different color for that. So we got I, our vector I, there. And then we have our standard unit vector J, which is there. Standard unit vector J, going vertically. So in addition to writing the component form, we can also write a vector as a linear combination. Linear meaning that we don't have squares, we're just looking at weighted sums. So a linear combination of our standard unit vectors I and j. And I and j are just in your x and y directions, or your horizontal and vertical directions. If you add another standard unit vector, then you're going to need to add another dimension. And so that'll be like your z direction. For like, if you have a graph that looks like this, where this one right here is like popping out of the screen. So that's, we're working in just like 2 dimensions right now. And then you have scalars that are the vertical and horizontal components. So these are weights. But this is just another way of writing the component in what we had in component form from before. And that makes sense because you have like when you're adding things together, for these, you're essentially taking like a 0 on the vertical direction when you're multiplying by I, and then you're taking 0 in the horizontal direction when you're multiplying by j. Right, so that's what is showing here. And so since we're looking at our vectors, where it kind of matters that we're dealing with our horizontal components separately from our vertical components, we still have all of the properties with our operations, like the commutative property, the associative property, because we're not doing particular like funny multiplication. Like, we're not changing the rules of multiplication or addition. We are just like breaking up what we're working with into 2 different directions at the same time. So it's a little bit more efficient in that regard. So if you have vector u plus vector v, that's the same as adding vector v plus vector u. Like, the order of that doesn't matter. We can group things together with our associative property of addition, and if we just add the 0 vector, that doesn't change our value. If you add the opposite of a vector, so if you have this vector going that way and if this vector going that way and the same magnitude, then they cancel out and you get the 0 vector. If you do scalar multiplication, it's okay. That doesn't change. When you're doing this scalar multiplication, that is happening with like a c times your vector v1, v2 in component form. So that's going to be c times v1, comma c times v2. With little squares. And scalar addition or distributive property, that works both with 2 scalars and with 2 vectors. And our identity property, where we're multiplying by our scalar of 1, doesn't change our vector, and 0 multiplying as our scalar gives us our 0 vector. That also makes sense, right? It's the product property. And these just make sense because we're looking at the same properties with our same operations that we did before, that we've been working with this whole time. There's a couple more things. If you have c is a scalar and you're looking at the magnitude of your scalar times your vector, then you can just scale up the magnitude of the vector without that multiplied, like without doing the whole like square root thing. You don't have to do this with the c times v1 minus c times v, this part, bad algebra. You don't have to deal with this as like cv1 squared plus cv2 squared. You don't have to do that because, I mean, like, well, factoring, right, this will come out, but just dealing with your vector, because you have like that's the same as that, because of that's c being able to factor out of both terms. And one other thing is the unit vector. So the unit vector has to have a length of 1. So how do you make sure that you have a length of 1? You can take the vector v, right, that's our vector v, and then scale it down, or scale it up, depending on how big it is, by how long it is. So if you take this vector and you divide it by the length of it, the magnitude of it, then you get a vector that's got a unit length. So the length of this is going to be 1. Because you're taking something and dividing it by like the magnitude of itself. So it's going to still have a direction, but you're scaling it by how long it is so that it'll give you a length of 1, but the same direction. Derivatives, they do work how we think they will. When we're looking at a derivative of our vector valued function, where we're getting out a vector because you have like 2 different directions that you're dealing with. And that's going to work for whenever your t allows it to be existing. So if we do have our derivative exists at that c, then we say that it's differentiable. And if we have our derivative on our open interval, then we say that it's differentiable on that interval. And it's so we can have differentiability at a point. We can have differentiability at a on an interval. And integration also kind of works how we think it will, in the sense that you can split up your components and deal with them separately, right? Because you have like a vertical direction, a horizontal direction with your I vector. You have a vertical direction with your J vector. So if you're looking at those kind of separately, you can still integrate, because we're just dealing with things in different directions, that they kind of have like independent vertical and horizontal movement. And definite integrals also work, so we don't have to have like a family of functions necessarily. We can also just find distinct numbers, and that is helpful. So thinking, I guess, less abstractly about what vectors are helpful for. Well, we want to have useful vectors, and for the most part, when we're looking at vectors, we're going to think about position, velocity, acceleration, and going kind of between those, because that's the utility as far as like derivatives and integrals for us, for the purposes of what we're doing. So if you're looking at the magnitude of the velocity vector, right, because dx dt, dy dt, those are the rates of change in the vertical and horizontal direction. So if you're looking at those squared plus and the sum of those and then root that, you're getting the speed, because it's the magnitude of your velocity vector. So the speed doesn't have the direction, but it does have the magnitude. So the speed is also like, that's what, if you're driving, then that's what's on your speedometer is your speed. So even if you're going backwards, you know, the speed still looks the same, that you can see that you're going like, I don't know, like 5 miles per hour in the backwards direction, you're still going 5 miles per hour. And then the length of this arc, where you're taking the speed and then you're integrating it on an interval, is how far your particle has traveled on that time. So it's like how far the like the step count is. So it's it's not like the displacement, right? Because if you go here and then you come back, then your displacement's 0. But the distance traveled is the arc length of how far you actually walked. So there's that. So let's look at some examples. So we have a particle, and we're given our x and our y components of it. So that's the position of our particle. So how do we find our velocity? We need our derivative of our x and our y components, and then we need to evaluate at time t. So our velocity in general is going to be defined by this vector where we're taking our derivative with the power rule. So we get 6t squared minus 10t. And then our derivative here, which is what, 8t cubed plus 3t squared. And so that's in general, but when we're looking at particularly when time equals 1, what do we get? 6 minus 10 is negative 4, and 8 plus 3 is 11. So our velocity vector at time t is negative 4, comma 11. So in the negative 4, 11 direction, that's where we're going. How do we find our acceleration vector? Can we take the derivative of velocity? Not the velocity when we evaluated, but our velocity when we're looking in terms of t. So our acceleration is going to be our derivative. That's a bad bracket. So we got 12t minus 10. That's not a comma, that's a minus. And we have 24t squared plus 6t. Okay, but we're still looking at when t equals 1, so our acceleration at time 1 is going to be 2 comma 30. So we're accelerating with this vector to 30. So you find the magnitude or length of a vector. If you're looking at your position vector, then what are you going to have? You're going to have this horizontal direction and this vertical direction, which give you a right angle. So this is your x of t, this is your y of t, and so that's going to give you your position vector. And the magnitude of that, you're going to do x of t squared plus y of t squared. What about your velocity vector? We talked about how this is the speed, right? But this is x prime of t and y prime of t. So our magnitude, which is the speed, is going to be x prime of t squared plus y prime of t squared. That's our magnitude of velocity, which is our speed. So this is the speed. And then, what about our acceleration? Magnitude of our acceleration vector. You guessed it, it's the second derivative. So we have x double prime and y double prime. So that gives us our magnitude of our acceleration, which is root x double prime t squared plus, we'll change to brackets, it doesn't really matter, but it looks, I guess, a little clearer, maybe. There's a lot of things happening. So that's our magnitude of our acceleration vector, and the reason that works is because that's a right angle, right? So we have Pythagorean theorem stuff. So think about this example. Find the magnitude of the velocity vector when t equals 3, given this stuff. Pause the video, try it out, and we'll talk about it. So it helps to kind of draw a little triangle. I feel like there's a lot of little triangles that happen in this course. So when we're looking at our x component and we're looking at the magnitude of velocity, that means that we need x prime, which is going to be 2t plus 5, and then y prime, which is what, 1 over t squared plus 4 times 2t. And so if we're looking for the magnitude of velocity, then what's that? What's the speed? Speed at time t equals 3. Well, first we need the general speed, which is root of 2t plus 5 squared plus 2t over t squared plus 4. And that was just by multiplying that 2t by that 1. And then we square that. And so now we can evaluate at time t equals 3. So speed 3 would be what? 6 plus 5 is 11 squared plus 6 over 9 plus, what is that, 4? That's a 4. 9 plus 4 is 13. And so we square that. And do we need to simplify that? It's okay. So that's a precise answer. We got that's our speed. So now we have a particle that's looking at cosines and sines, and we're looking from 0 to 2 pi as our times. The path of our particle intersects the x-axis twice. How are we going to write an expression that represents the distance traveled by the particle between the two x-intercepts? Well, first we need to figure out where those two x-intercepts are so that we can write our integral from those two bounds, but we don't need to evaluate, so we just need to make sure that we have the right things in our integrand. So pause the video, think about that, and then we'll talk about it. And we intersect the x-axis when y is 0, so set y equal to 0, and we get 1 minus 2 sine of t equals 0. When does that happen? When sine of t is a half. And when does that happen? When is sine 1/2? And if you don't remember, then think about it. When is the y value 1/2? That's going to be at pi over 6 and 5 pi over 6. Right there. And so those are our bounds. So we're going from pi over 6 to 5 pi over 6. Okay. Now, what do we need to put into our integrand? Well, we're looking for the distance traveled. So the distance traveled is going to be our arc length. And the arc length is using our derivative, so we need to take our derivative of x with respect to t, and what's that? That's positive 4 sine of t. And then our derivative of y, and I just wrote through what that was, so y prime of t is negative 2 cosine of t. And so that's what's going that's what we're finding the magnitude of, our velocity vector. So that's 4 sine t squared plus negative 2 cosine of t squared. And we're integrating with respect to t. It says do not evaluate, so we're not going to evaluate. But if you were going to try to evaluate that, you should probably put that in your calculator. Don't forget about Math 9. It is your friend. So earlier this year we did learn that when you have a particle that is at rest, then its velocity is 0. And if you have a particle moving along a curve, the particle is at rest when its velocity vector is the 0 vector. That makes sense. If you don't have vertical or horizontal motion, then you don't have motion. So look at number 4. Particle moves in the xy plane so that at time t its position is given by these two functions when t is greater than or equal to 0. Find for what values if t is a particle at rest. So try that out. Pause the video. Try it out. So take some derivatives of your x and your y. Set those equal to 0. What do you get? We can factor out a 6 here, so we get t squared minus 5t plus 6, and that's factorable. So then we get 0 is, what, t minus 2, t minus 3. So at time t equals 2 and 3, our our particle is not moving in the x direction. And then for the y direction, when is that happening? Well, we can factor this. So we get t minus 2. And then setting those equals 0, we find that's when going to happen when t equals 0 and t equals 2. And where do we have overlap? At 2. So what values of t is a particle at rest at time t equals 2? The particle is at rest. It's helpful to answer the question using words from the question. So for what values of t is a particle at rest at time t equals 2, the particle is at rest. Just copy half of it. Alright, so try number 5. Particle moves in the xy plane such that its velocity vector is this. At time t equals 0, the position is 7, negative 4. So find the position of the particle at t equals 1. So what are you going to do? This is your velocity vector, so think about it. So to go from the velocity to the position, we need to integrate. So let's integrate. And what do we get? We get t cubed minus 2t squared plus c, and 2t to the 4th plus 5t plus c. We're given at t equals 0, the position is 7, negative 4. So at t equals 0, so we plug in 0, we get 7 out. So that's 0 minus 2 times 0 plus c. So that means that c equals 7 here. So then our position is x of t is t squared minus 2t t cubed minus 2t squared plus 7. And then over here, plug in 0, and we get negative 4. So that means that c equals negative 4, and we have our position in our y direction is 2t to the 4th plus 5t minus 4. And then to find the position of the particle at time t equals 1, just plug it in, and you should get 6, 3 by just plugging in 1 here and plugging in 1 there. Alright, so this is, we got our position with our vector where we have sine of t cubed and cosine of t squared. Those are kind of gross, so we're probably going to use a calculator. At time t equals 2, we have the position 7, 4. So how are we going to write our equation for our tangent line to the curve when t equals 2? Remember, for our tangent line, we need a point and we need a slope. We do have the point. It's at 7, 4. So we need our slope. And our slope is our dy dx. And what's that? That's dy dt over dx dt. And so how are we going to find that at time t equals 2? That's going to be what, like cosine of 4 over sine of 8. And you should probably put that in your calculator. And so then you get something like negative 0.661 question mark. So then your line is going to be y minus 4 from there equals negative 0.661 times x minus 7, which is from there. How are you going to find the speed at time t equals 2? Speed is going to come from the magnitude of your velocity. So that's at time t equals 2. That was cosine of, sine of 8, and then square that, and cosine of 4, and square that, and that's going to give you a number, and that number is probably 1.186 stuff. AP exam likes rounding things to the thousandth. That's fine. I don't think they'll be too upset though if you just leave it like that, unless they actually want a number. So the speed of the particle at time t equals 2 equals this, which is that number. For value of t between 0 and 1, does the tangent line to the curve have a slope of 4? And then find the acceleration vector at that time. So when is the slope going to be 4? When cosine of t squared over sine of t cubed equals 4. And when is that going to happen? Do that in your calculator. Like solve that probably using the y equals and plugging in 4, and then another y equals for cosine of t squared over sine of t cubed. Probably use x though. And then find the intersection of those 2 points. Once you find that point, which is t equals 0.61648 and so on, store this as some variable, probably not x. Store it, I would maybe put it in like a. So like do the alpha and then a. So you can store this number. And then evaluate your acceleration, which is your derivative of velocity. And you can evaluate it at this a that you stored it as. You could do your derivative using the calculator, or you could do this derivative by hand, because the derivative is relatively straightforward. Like, it's just a chain rule, right, of sine of t squared times 2t and that's the y component. So we have our x component is going to give us cosine of t cubed times 3t squared, and our y component is going to be negative sine t squared times 2t. And then evaluate that at this t that we solved for. And then you should get a vector that's something like 1.109 and negative 0.457. If you need help with the calculator usage, please let me know. And then finally, how are we going to find the position of our particle at time t equals 1? Remember, we need to integrate, right, to find our position from our velocity. And you got to integrate your x and y components separately. So try that out, and then we'll talk about it. So when we're looking for our position at time t equals 1, but we only know about time t equals 2, then we need to go from time t equals 2's position and then backwards. How are we going to do that? Well, we can integrate. So we can go from 1 to 2 of our x prime of t direction, and going from 1 to 2 of our y prime of t direction in our vertical direction. And so what do we end up with? Well, we end up with our position at time x equals, that's going to be from x equals 2 minus x equals 1, right? And since we're solving for this, that's what we're looking for, then we should probably try to get it by itself. And how do you do that? Well, you shuffle some stuff around, so you end up with x of 1 equals x of 2 minus this integral from 1 to 2 of x prime of t. And now on the right-hand side, we have a bunch of things that we know. Because x of 2, that's going to be 7. Our position was 7, 4, right? Minus this integral, and we're probably going to use our calculator for this integral, but you don't necessarily have to. But that's our derivative of position, that's 2, which is velocity, which is what we're given. I would probably use a calculator. of sine of t cubed. And once you have this sine of t cubed, just plug that into your calculator, and you get like 6.782. And if you didn't, then make sure that you subtracted 7 minus this integral. And so that's your x position. And for our y position, it's pretty much the same thing. We just do it with our different functions. So this is going to be y of time 2 minus y of time 1. And then to solve for y of time 1, we just do some algebra, like move the y of 1 over here, subtract this on both sides, so you have y of 2 minus your integral from 1 to 2 of y prime of t dt. And what is that going to give us? 4 minus your integral from 1 to 2 of cosine t squared. Plug that in to your calculator and you get 4.443. So actually this value is going to be negative, so when you're taking 4 minus this negative value, you're going to get out a bigger number, and that is okay. So our position of our particle at time t equals 1 is our two components, where we have 6.782, comma, 4.443. Box around that. It's not a good box, but that's the position at time t equals 1. Alright, try this last one, where you're looking at a particle with this velocity vector, figuring out, do we have horizontal motion to the left or to the right? Remember, left is negative, right is positive. Find the slope at time, slope of the path. Find the speed, or at what time is our speed equal to this, and the magnitude of our displacement between time 2 and 3. So try that out, and then we will talk about it. Pause the video. Pause. If we're looking for the horizontal movement of our particle, is it left or right at time t equals 2? Well, we could like evaluate v of 2 and then figure it out from there, or we could just look at our x component. So x prime of t is sine of t squared, so x prime of 2 is sine of 4, which is something like negative 0.7568 stuff, and that's less than 0. Thus, because we have to explain our answer, the horizontal movement is to the left, because x prime of 2 is less than 0. How are you going to find the slope of the path of the particle? That's going to be what our change in our y over our change in our x. And so that's going to be y prime of t over x prime of t at time t equals 2, which is e to the cosine of 2 over sine of 4, and that's calculator negative 0.8715 stuff. And so that's going to be our slope. And that makes sense, right? Because e is going to be e to some power is always going to be a positive number, divided by this sine of 4, which we found was a negative number, so a positive over a negative, we have a negative number, right? So our slope of our path is negative 0.8715. How about this? At what time t is our speed 2 units per second? So the magnitude of velocity, when is that going to be 2? So that's going to be at when our magnitude of v equals 2. And when does that happen? When we have root sine of t squared plus e to the cosine of t squared, when that equals 2. When does that happen? Let's look at this. So I graphed 2 and root sine of x squared plus e to the cosine of x quantity squared, and the square root of all that. And so then I looked at a graph, made sure that my window was something reasonable. I wanted from 0 to 4. And so there's the graph. And then in order to find the intersection, we do like second trace to get the calc. Intersect, which is 5. First curve, I'm just going to move over here though, so I get closer to where they're going to intersect. Second curve, enter, enter, and then I hit enter, and my intersection is at this x value. And so that is what I'm writing, where we have when t equals 0.89762239 seconds. And then what is the magnitude of the displacement of our particle between time t equals 2 and time t equals 3? So set that up, and we'll see how you do. Magnitude of our displacement, and that is going from time t equals 2 to time t equals 3. So you might be tempted to find the arc length. But is that going to be the magnitude of the displacement, or is that going to be the distance traveled? So don't be tricked that the arc length is going to give you your answer, because it's not. So the magnitude of our displacement is going to be the difference between our beginning and our end points. So how are we going to figure that out? We need to evaluate our position at time t equals 2 and our position at time t equals 3. So we need to integrate these. Do we have a position? No, we're just looking at the difference between those two positions. All right. Let's see. So we have our velocity is sine of t squared, and our e to the cosine of t. And our displacement is going to be how far we go from 2 to 3 on our vectors in our x and our y direction. So we have sine of t squared and e to the cosine of t. Alright, so let's do that in a calculator. So that's going to be, and then we're taking these and magnituding them, right? And so what do we end up with? We get some stuff that we did in the calculator. And so, probably should have stored some of these. So I'm going to store this, or I'm going to square this value, and then I'm going to store it in B, and then second enter to get back up to what I had before, second enter again, and one more time. So that's our first one, and then square that, and then I'm going to store that in A. Oops. So I'm going to store that in A. So now I have A plus B, which were, A was this, and B was that. And add those together, and then square root them. Second negative sign to give the answer. And so we got that. That is the magnitude of our displacement negative 0.4718. 18 is 2, and that is our displacement, magnitude of our displacement of our particle from time 2 to time 3 of the particle that's moving like this. We don't have units, but that's okay. All right, so to sum up, when we're looking at vectors, that's a magnitude with direction. If we're looking for magnitude of things, that means that we're finding a scalar value, or how big a vector is. Position, velocity, and acceleration are what we're going to be generally looking at. Look at your x and your y components. Plug things in. Don't forget calculus works. Our fundamental theorem of calculus, our derivatives, all the power rules, those all still work. Don't forget about geometry skills that you know, and speed is the magnitude of velocity, and position has magnitude as well, and so does our acceleration vector, and our arc length is our distance traveled, but that's not the same as our displacement. Calculus works the way that we think it will. Unit vectors are helpful, where you take the vector and divide it by its magnitude, so you get a vector of length 1 that's in the same direction. Our arithmetic works the way that we think it will, and we can have different ways of writing vectors. So we have, when we're typing, we use bold. When we're handwriting, we use the little arrows. And we have component form, where you're looking at U1, U2, or you can also have in our linear combination form, where you have U1 number times your unit vector I, plus U2 scalar times our unit vector J. And that just about does it. All right. That's our vectors in calculus. Bye.